Hello guys, welcome to Learn Extra Live. Grade 12s, it's finally your turn for some physical science, guys. I hope you guys are ready. Thank you to Macmillan for sponsoring such a phantasmical show. I know it's not a word, but it's my word for today, so I'm going to continue using it. I've missed you grade 12 so much. I've been telling everyone else. I haven't told you. I've missed you guys. I hope you guys are already on the page. Most of you have been here since the grade 10 show and chatting to me. I really appreciate that, guys. Call your friends, tell them to join us as well, because today we have Tracy in the house and we are doing rates of reaction. Please tell us a bit of what we'll be doing today, just a bit.
A snippet. Well, besides the fact that I'm going to try not to blow up the studio
Okay.
a little bit later. Hopefully I won't.
Or you can.
Might get a little messy, but hey, my kids at least will go, no, that's the teacher we know. I'd say in love, but maybe not. But we're looking at rates, so we're going to look at why reactions happen in terms of their speed, and then we're going to look at the factors that affect that, which is what I'm actually going to demonstrate, 3 of the factors.
Awesome,
So,
thank you. So you guys heard it's going to be a jam-packed show with lots of, hopefully stuff will blow up and we'll see some cool things today, because I like seeing cool things and I know you guys like it too. So jump onto the page, facebook.com/learnextra, as well as our Twitter handle, guys. Make sure that you are here chatting to us, asking any questions that you need to ask. Guys, we're here for you. So basically, for the next hour, it's just you and us. Don't move off those seats because there's a lot for us to get through. Over to you, Tracy.
Oh, thank you. It's nice to be back with you.
I know.
I haven't seen the grade 12s for a while, actually, so it is very cool. Like I said, we're going to be doing rates of reaction. It's actually such a nice section. And what we're going to do is we're going to define and discuss what is the rate of reaction. We're going to look at collision theory, extremely important. We then are going to demonstrate some of the factors that influence the rate of reaction, and then we're going to discuss why. Now, unfortunately, I can only show you 3 factors. There's actually 5 that we need to look at, but we're going to explain exactly why they affect the rate the way they do. Okay? But now the first thing we need to do is define what we mean by rates of reaction. Now, the first thing we've got here is that the rate of a chemical reaction is a measure of how quickly or slowly a chemical reaction takes place. Now, that makes sense because we're talking about rate, okay? And it's the same as when we say, well, power in physics is the rate at which work is done. So we're saying this is the rate at which the reaction happens. So we're looking at how quickly or how slowly. We know some reactions are really, really slow and some reactions are just really, really fast. We're looking at how that happens, okay? Now, there's a couple of ways rate can be measured. We can put it as a unit, so we can say, well, the rate was 20 grams per second or 20 grams per minute or per hour. There's no set unit to rate, but it all depends on how we're measuring it. And how we measure it depends on the reaction itself, okay? So we can measure rate in 3 ways, essentially. 1, we can measure the rate at which a gas is produced, okay? And the way that we would do that, now, today I'm going to show you a reaction where we're going to produce a gas. We're going to produce carbon dioxide, I think. Yeah, we are. But I'm not going to collect it, all right? So we're not going to be able to measure the rate of the reaction based on the amount of gas produced because we're not going to collect the gas, okay? That would mean that we do it in a closed system. So say we're collecting hydrogen gas, we're reacting magnesium, say, one of your metals with an acid. The acid and the metal goes into a test tube, for example. The test tube has a stopper on the top with a delivery tube, which then goes either into an upside-down burette, okay, which allows water to go down because that would be a very small amount of gas, or into a gas syringe, which has the plunger, which is able to move, okay? And then we can see the volume change, and we can make a decision. Something like magnesium and hydrochloric acid, it's a fairly quick reaction, so we would take measurements every 10 seconds, every 15 seconds, etc. But if it's a reaction that's quite slow, you know, taking every 10 or 15 seconds, and you go, okay, 10 seconds gone by, oh wait, it hasn't moved. You then do it per minute or per hour, depending on the reaction, okay? And then we would write the rate in terms of volume, okay? Gas produced is very difficult to measure in grams, but there is a way. It's just a little bit more difficult, okay? But we can do that. The second way is to look at the rate at which mass is lost. But please note here, I've said in an open system. This would require a system where a gas is produced. So if we looked at the same reaction with the magnesium and the hydrochloric acid, and instead of just collecting the hydrogen gas, because that can be quite difficult, is we put it, say, in a conical flask on a scale. Okay? We put it on a scale, we zero the scale at the beginning of the reaction, or we don't have to, but we zero the scale, then it'll go backwards. But we can use it, put it on a scale, and we watch the mass change. Because as the mass changes, it means that the gas is escaping. And that is a measure of the reaction. So we're looking actually at how fast the gas is being produced. We're actually looking at the mass of the gas produced. But we would take it from the loss of mass, okay? The third way is the rate at which color change takes place. This one is actually quite important. And if you look at the notes we've put on the site and on Facebook and stuff, you can go to one of the links where, and it's the first link I put on there, for the reaction of sodium thiosulfate. That's actually a really, really important reaction that you must be able to explain. Okay, sodium thiosulfate, when we react it with hydrochloric acid, turns milky because we create sulfur. And in fact, we measure, because there's no gas produced, so we can't measure mass loss. We can't measure gas produced. So we've got to find another way of measuring how fast or how slowly the reaction takes place. So what we actually do is we draw like a black cross on a piece of white paper, and we put a beaker on top of that, and either the sodium thiosulfate's already in the beaker, and then we add the hydrochloric acid, or we do it the other way around. It doesn't actually matter. And then we time until the cross disappears. This is a really nice one to actually do in a classroom, because when I do it with my kids, is we put the black cross onto the overhead. So I'll do it with an overhead marker, and then they watch until they can't see it. It goes a little bit yellow. We're creating sulfur, so you see the yellow for a while, and you know the reaction has finished or has gone to the same degree of completion. In other words, we've made the same amount of sulfur once we can't see the cross. It's a really nice way of measuring a chemical reaction. We're not going to do that one today, but it's also a nice one. You can see it with the links, and it makes it really easy. So there's lots of ways we can measure rate. The rate then gets described as mass per time unit, so grams per second, kilograms per hour, grams per hour, can be a volume per time period. So it's a volume or a mass per time period, okay? And we can either look at the products that are produced, or we can look at the reactants that are used up. Doesn't actually matter. It's one of those things that are really, we define it as the rate, but how we measure that rate is really very, very open, okay? But now we go, one of the key concepts here is, how does the chemical reaction happen? So what needs to take place, besides the fact that we need to put the reactants in the container, what actually has to happen for any reaction to happen? And that's where we get to collision theory. Now, collision theory actually has three very, very important parts. The first one I actually haven't written on the board, but it is in the notes, is that number one, it's exactly what it says. The particles must collide, okay? In order for chemicals to react, the molecules or the atoms involved must hit each other, okay? Those collisions are really important. If I have a hydrogen atom or molecule over here and an oxygen molecule over here, and they are not going anywhere near each other, never will they make water, okay? They need to collide. Their orbitals and their molecules, their electron shells need to overlap, because unless they overlap, there cannot be a sharing of electrons or a transfer of electrons, as the case may be. No chemical reaction will take place. So first and foremost with collision theory, it's exactly what it says. The particles must collide, okay? Number two, the particles must collide with the correct orientation. This is not random. So what I've done is we've got a little bit of an illustration, okay? And we have, let's call this over here, let's call this iodine, and let's call this hydrogen, okay? And the hydrogen and the iodine molecules come along, and what happens when they collide? So number one, they've collided, brilliant, okay? But over here, sorry, that's the iodine, it's way too big for hydrogen. So here's the iodine, there's the hydrogen, and we look and we go, there's a problem. Only one iodine has collided with one hydrogen. Nothing's going to happen here because the ones on the outside are going, okay, you know what, you guys don't want to play ball? Fine. We're not going to have a chemical reaction happening. Okay, because they're like Siamese twins and they're going, actually, we're quite happy with each other. We're going to move away. No reaction happens. And the hydrogen and the iodine move away like nothing happened. Okay, that collision is not what we call an effective collision. Because what's happened is they've come together, they've collided, which is what we needed, but they haven't collided in the correct way. Okay? So it's like you meet someone, but the circumstances just, you know, ladies, you know what it's like. You're looking for your date, for your matric dance, and you see that hot boy down the road, and yet, you know, it just never seems to be right. You know what I mean? The circumstances aren't right. You aren't wearing the right clothes. You know, you got a cold, so you all don't sound nice. He's there, but it just doesn't work. So you never actually connect. Okay, but one day all the circumstances are correct, you connect, and hey, we're all very happy. Then, if however, and this is the correct orientation, here's my iodine, there's my hydrogen, now they collide. Now watch what's happened here. If I draw a line over here, can you see I could actually move these away, and a hydrogen, and we're actually making hydrogen iodide. A hydrogen atom can now come off with an iodine atom, and a hydrogen atom can come off with an iodine atom. They both have friends. With the top one, if this hydrogen and iodine came off, we'd have a little iodine atom floating around and a hydrogen atom floating around, and they don't like that, okay? Remember, they're diatomic. They need to have friends. They don't like to be on their own. Whereas here, when they've collided with the correct orientation, okay, so they collided in exactly the right way, they can move away from each other and they're happy because now they've connected. So, collide, correct orientation, but the third one is they must collide with sufficient energy. Now, this one's quite important. That's what we call the activation energy. That's a term you've definitely heard before grade 12, so you did that a lot in grade 11. Remember that for any bond to be formed, we have bond energy. That's really what I'm looking at here. This sufficient energy is the activation energy. Now, for some reactions, this is tiny. So it doesn't take a lot of energy at all. So magnesium in hydrochloric acid doesn't take a lot of energy. The reaction happens really quickly. Hydrogen and oxygen atoms, and we're quite grateful for this, that has to take place with a lot of energy. It's why we have to burn the hydrogen and oxygen. I'm quite grateful that that needs to happen because otherwise we'd be constantly having water formed in the atmosphere all around us because we have hydrogen and oxygen in the air around us. That would be a little annoying. Okay, so we're glad there's lots of energy needed. This activation energy is actually really important because if I can change that or I can increase the amount of energy in the substance, I can make the reaction go faster. I can do something about the energy part, okay? In terms of the correct orientation, when it comes to the rates of reaction, the best that we can do is try and make the molecules collide more often. So think about, just in terms of statistics, the more often we collide, the more likely there are to be correct collisions. It's the same as, and I'm not saying that you should do this, but if you play the lottery, the more often you play the lottery, the better your chances are of maybe winning. Or the more lottery tickets you buy on a certain weekend, the more likely you are to actually win. Whereas if you go and only buy one set of numbers, the chances are quite slim. You might still win, but it's quite slim. So we need to increase these collisions because the more collisions we have, the more likely they are to result in a chemical reaction, okay? And I think, Kat, that's a good place to take a break.
I think so.
And then I'm going to go and get ready.
Get ready for the explosion.
Yeah. Well,
okay.
Hopefully no explosion, but yes.
Okay, get ready for the almost, but not really
Yeah,
explosion.
it'll be fun. It'll be exciting.
Okay.
There'll be colors and fizzes and things.
Okay, so you guys heard that, right? So make sure that you do not leave those seats. Guys, I mean it. It's going to be awesome when we get back. So stay right there. We'll be back just now.
Yeah.
Welcome back, guys. Of course, we are doing physical science with Tracy and I. If you have just joined us, we are doing rates of reaction, guys. It's been awesome so far. So if you have just sat down and you just tuned in and you were like, oh, wow, hey, well, you've joined us at the correct time, guys, because the show is about to blow up. Without further ado, I'm going to...
Well,
Tracy, are you ready to us?
we're hoping not blow up. I mean, we have had some concern with me using acids, but it's okay. I am qualified.
Okay.
Anyway, so guys, we're going to look at rate of reaction. And this is actually something, except for the last one, that you really can do at home. All right, just ask Mom before you start using her fizzy tablets. What I have is you know, fizzy vitamin tablets. There's a whole range on the market. Doesn't actually matter which ones we use. The reason why we use these is, one, it's going to be a nice color, and two, it's a nice color.
Okay.
And it's easy. So the first thing we're going to do is we're going to look at how surface area. Okay, so it's the first thing, and I've got it on the board, and it's in the notes. We're going to look at surface area. So what I'm going to do is, into my glasses, I'm going to put some water. Okay, and we're going to sort of try and make it about the same amount. Oops. Yeah, John is now very worried about me messing. It's okay, this was just water, it's fine. Okay, so we clean up my mess. This was just water, it's fine, it won't damage anything.
No.
Okay, so the first thing we're going to do is we're going to go, okay, we have our tablets. I'm in the one glass, and we're going to do it together so you can see the rate. We would time it, but we're not going to worry about this. We're going to use the one whole like it is. But then the other one I'm actually going to break up. And what I'm doing by breaking this, okay, so I'm putting it into smaller chunks. And you know what, I know exactly what's going on in your head. You're going, oh, we've done this when we're in a hurry. This is actually why, and I'm not sure if I'm going to get in trouble for this, but things like grandpa headache tablets, well, no, the powder.
The powder one is
the powder,
much faster.
that's why it works so fast, is because it's in powder form, okay? So anything that you put in powder form should go faster. So we're just going to break this up. It's also the reason why we do this, because I can actually break it up. So here we go. Big whole tablet, one in powder form. We're going to put it into the water at the same time, and we're going to see what happens. Now, if Abram can focus on the glasses, Wilson, sorry, Wilson.
No.
I think I should just go home now. Anyway, you can see that the one which is this side, the one where we had it in chunks, it's gone much faster. You can already see it's a nice darker color. This one, you can see, well, on the chunk one, you can see the gas forming really, really nicely. In fact, that's gone really quickly. Whereas the one where we had whole, it's taking a little longer. And if this was me leaving for school in the morning, I would be like, okay, hurry up. So I just actually, when I have to take these, I just, you know, change it a little bit just to make it go a bit faster. But unfortunately, I don't think you can actually hear, but it's fizzing away quite nicely. And if we look very carefully, I hope we can actually focus in quite nicely. This one's actually almost finished. And there's only tiny little pieces left. This one still has quite a big chunk. Has a very big chunk in it still. In fact, I'm going to put it that way. I don't know if you can see, but there's a chunk of it right there that's still busy reacting. This one, no, it's pretty much done. Okay. Now you've got to say, all right, so we increased the rate of reaction. This one was slower when it was whole. This one was faster when I made it into small little chunks. And in fact, what I did with the chunk one is I increased the surface area. And I know some of you are going, no, you didn't. You made the pieces smaller. I know I did. But in science terms, I actually increased the reacting surface, which I'm going to show you in a diagram a little bit later on. So this was actually quite important. The more finely ground the surface is, and this only works with a solid, okay? I can't change the surface area of a liquid, and I can't change the surface area of a gas. But the more finely ground it is, the greater its surface area, the faster it goes. So we've got to be careful. And in fact, when we look at reactions in industry, it's exactly what they consider. Because magnesium powder, as a good example, if in your classroom, when we demonstrate the burning of magnesium to you, we use magnesium ribbon because I can control that. If I had to use magnesium powder, it would be completely uncontrollable because it's too fast. So we don't do that, okay? That was fairly straightforward. The chunk one is pretty much done. The one with which was in the big hole ones, is still going. It's taking a while to catch up, but eventually they will be the same. First one, easy enough. We're done. The nice thing about an experiment like this, though I'm not going to do this because it's probably a little too concentrated for me, is you can drink the contents. Quite safe. Okay. Now, we get to the fun one. Well, second fun one. Now we're going to look at temperature. So what I'm going to do is I'm going to add some water to this glass, which has got ice in it, which is going to make it cold. Okay? And I really am just using ice water because I want it to be significant in the temperature change, okay? So that's going to be really cold. We'll take the temperature in a second. And then what I have in my mug is I have some warm water. Okay, so there's the warm water. And I know it's difficult to see. Well, you can see some of the condensation, but let's just prove it to you. We'll take the temperature, and we're just seeing, and it's going up still. And I don't know if we can see it on camera. I'm not letting it touch the sides, but it is round about 43 degrees. So that's quite warm, okay? So you believe me that it's warm water. This would make terrible coffee, but it's okay. Would be horrible to drink. Anyway, now we put it in the ice because we can, and let's put a little thermometer in our nose that it's winter, and there's a very big significant change in temperature, and it's still moving. It's about what it is outside, I think, at the moment. Winter definitely has arrived this week. Yep, no, it's about 9 degrees. So, sorry, I'm being really horrible to the wonderful camera crew. Sorry. Anyway, so very cold, warm. This time, I'm going to use, because remember, whenever we do a chemical experiment, guys, we can only change one factor at a time. So I'm going to use both of these whole. I don't want to crush them because I know crushing them increases the rate. And I know that by crushing it and then putting it into hot water, it could be a little messy, okay? So I'm going to use them whole. The ice blocks do make a little bit of a difference, but not much, so we're not going to stress about that. So I'm going to put these in, and then we're going to see what happens, okay? So you ready? And away we go. And even better there in the surface area, you can see how nicely the warm water is going. It's actually making a really nice, it's bubbling quite nicely. At least it wasn't as hot as it was earlier, then it would have just spilt everywhere. And in fact, I don't know if Wilson can actually go in close enough, but I don't know if you can actually see the gas that's been formed. Okay? That gas is carbon dioxide. Okay? That's what makes you burp.
Ew.
After you know the antacid adverts, and there's one particular brand that says, it's the burp that makes you feel better. It's because you're making this.
Oh, okay, I get it.
And it doesn't actually, but let's not go there. Okay, because it's not really, it just makes you feel like you're feeling better.
But you're not really.
Not really. That's why boys use it. Girls use bicarb. Bicarb's actually much better. But that's a story for another day. This you can see so nicely, okay? Because you can see the difference in the color. This one's already a nice darkish orange. This one is still very yellow. I don't wonder where it's gone. Actually, it's sitting right there at the bottom. This one, no, it's finished already. The tablet is completely dissolved in the warm water. It's gone. It's very happy. You can see the gas bubbles. I don't know if I'd want to drink this personally.
Oh.
Well, it's lukewarm. It's just... Yeah, it's personal. Anyway, maybe not. This one looks more appetizing, let's be honest.
That one just looks like an orange drink.
It does a little, hey, with the ice cubes.
Yeah.
And this could take a while. In fact, if we leave this, the thing with rate of reactions, this is what you need to understand here, grade 12s. Even with the surface area, these reactions will go to the same place. So they will end at the same place. In other words, I will make the same products. I'm just changing the time frame for making those products. If you were paying attention, even with the surface area, I used the same amount, same tablet, same mass of the tablet, same volume of water, okay? Here, I'm using the same volume of water, essentially, with the same mass of tablet. I've just changed the temperature. So I'm not changing the amount of product. I'm just changing the time it takes for me to get there, okay? Now remember, in the first session, we said we could also look at the color change as being an indication of rate of reaction, which is actually what we're doing over here. So we're looking at the color change, okay? This one, shame, is still going. I think the tablet's actually hiding now because it's going, okay, it's gold. This one, all finished. And in fact, even the bubbles in the warm water are starting to disappear because it was much warmer, so the gas is escaping much faster. So we're actually, this has still got lots of bubbles. This could take all night, so we're not going to actually wait for it to finish, but there we go. Okay, now this is going to be the fun one. This I've done plenty of times. The next one, not so much. Anyway, we go back to our glasses. What we're going to do now is we're going to look at concentration. We've used water and our fizzy tablets. We make our fizziness, that's easy. We can drink these products. What I'm about to do, you cannot drink these products, just so you know. And I'm not even going to try, so don't try.
Okay.
I'm just saying. What I have over here is I have 2 little beakers, which before I came into studio, I made 2 samples of sulfuric acid. Now, the one is marked, and that's really important because if you look at these, and this is a good technique in terms of lab work, is they look the same, okay? And this is why you mark your beakers or your equipment, because you need to know which is which. One is a fairly concentrated sulfuric acid, and one is a more dilute sulfuric acid. I used very concentrated sulfuric acid to start off with. We don't dilute it in studio because it actually is very exothermic. It gets very, very hot, and we need to make sure that I don't spill it all over myself, which is always important. Sulfuric acid is one of those corrosive acids. It's a very important industrial acid. We make lots of it in South Africa. In fact, it's why you have to do the contact process again, because we make sulfuric acid. Okay? Important acid. Now, the beaker that's on my left is my dilute acid, and I realized that because it was called water, just so I remembered. And the one on my right, which would be your left, is my concentrated acid, okay? I'm not going to use as big a volume in the liquids as I did with the water because I'm not 100% sure how much gas we're going to get off this, okay? And I would rather not mess the studio, if that's okay. I've got a feeling I might get fired. Just saying. And we're also a little worried I might spill it all over me.
Don't do that.
Okay, and I'm doing a big no-no. Your teachers would kill me. I'm not wearing a lab coat, okay? You really should wear a lab coat. But it's okay. We'll forgive you.
Your t-shirt looks better for today, but now
No, it does. It
we've
does.
taken it. Okay.
I have a really groovy lab coat with a little person buying stuff up for school. And my kids all laugh and go, yeah, that's about right. So, we're going to put some sulfuric acid in that one. That's my concentrated one. And then, once again, I want to try to keep the volumes about the same. So now I'm going to put the less concentrated one in there. Okay. I'm not using as much. I don't actually want as much product. Now, remember, I said it's all about keeping your all the rest of your variables the same. So these are the same temperature. They've been sitting in the studio. They're both the same temperature. I'm keeping these whole. I don't want to break them just in case. So now we're going to see more concentrated, less concentrated, and there we go. Okay, not so bad.
Aww.
Oh, I know. That was a bit, sorry. Maybe I should have used more. Smaller container.
Yeah.
But you can actually see quite nicely with the concentrated one how nicely it's bubbling. In fact, if you think back to the other ones you've seen, this one's bubbling lots. Because it's an acid with a carbonate, we get lots and lots and lots of carbon dioxide coming off. Really not so much here, but they're still happening quite quickly. Even if you compare it to the temperature ones, okay, and the ones with the surface area, we'll talk about those in a second, but they're actually going quite nicely. This one's still, if you look really carefully, you still get nice foam on top. It's all the gas, those gas particles from the carbon dioxide. That's what's actually creating all that foam, or the bubbles that you see at the top. It's actually almost finished, and it's much darker. This one is slightly different in the amount of product we get. So we look at it. It's a much darker one. I don't think there's any. No, the tablet's right on the top. You won't be able to see it. I don't actually know where this one is. No, this one's hiding. It's decided it doesn't want to play just yet. Look how dark the color is, okay? And this is actually quite nice for you to see, because if you look at the different volumes of liquid that I used, the color changes actually, which is also really nice because that comes through the concentration of our products. So one of the things that we're making as a product is whatever the substance is that creates this orange color. So the coloring, the more water we have, the less concentrated that color is, so it becomes a lighter color. And in fact, the ice is getting there. I don't even think the ice is finished yet. No, in fact, the ice still has a little bit of a tablet down the bottom there. My concentrated acid, it's actually really, really dark. I will form slightly more product with the concentrated acid because I have more particles, but they're going off quite nicely. I'm glad I didn't break anything or blow anything up. Probably if I'd used a more concentrated acid, it would be a little bit more exciting.
We could make a bit of a volcano here.
Yeah, yeah, I get into trouble for making volcanoes, eh? I'm just saying, because generally it's quite messy. You've seen the ad with the volcano. We don't want to do that. And I might spoil my shirt. I like my shirt. Anyway, moving on. The point is, the more concentrated it was, the faster the reaction went. And still, even with the less concentrated acid, it's gone faster than the other two went. Much, much faster, because it's an acid, not water, so the reaction takes place faster. Just naturally, it's going to take place faster because we're using different substances. That's also important for you to see, because when it comes to the speed of the reaction, there's things like the nature of the substances which we can do nothing about. So the speed at which it reacts with water is different to the speed it reacts with an acid, simply because we're using an acid. And the acid just has things that react faster. Think about the reactions when you have the metals in water. Lithium is not quite as exciting as potassium, because potassium, just by its nature, reacts faster and is more exciting, okay? Now, we're almost ready for a break, and what I want you to think about, because one of the things, we've seen this, so we went temperature, we went surface area, and we said, well, if I increase the surface area, I increase the rate. We went with the temperature, and we said, well, if I increase the temperature, I increase the rate. And then we had concentration, and if I increase the concentration, I increase the rate. But we have to be able to explain this. So in the next break, in your own minds, think about what we saw about collision theory and see if you can possibly come up with an idea of how we would explain why these happened the way they did, why the different factors increased the rate. Okay, and I think it's a good time for a break.
I think it is. So guys, there's lots to think about and lots to type. Write it up for us, guys. Send it through to us, just so that we know that you guys are on the right track. See you right after this short break. Welcome back, guys. I really hope that you guys saw that awesome, without the explosion, awesome experiment that we just did. It really was cool. The studio smells nice and orange. I know that's not a smell, but it smells orange in here. I hope you guys actually did catch that, because it was really great. And you've taken notes on the different things that occurred at the different stages. I hope you guys really had that. And Tracy, you gave them something to think about. Please, may you tell us what that is.
I'm glad you're having a good day like me. Anyway, good. I hope you're thinking about it, and it looks like from some of the questions coming on Facebook that you have, which is really, really good. So let's think about the fact that we said in the collision theory, 3 things have to happen. The particles need to collide, they need to collide with the correct orientation, and they need to have sufficient energy, okay? So if we go straight to again, I've got it in different order, so let's talk about temperature to start off with, okay? With temperature, remember, temperature is defined as the average kinetic energy of the molecules, okay? Now, whether that's a gas, whether that's a liquid, it doesn't matter. It's the average kinetic energy. So, if I increase the temperature, and I did it of the water, I didn't have to increase both temperatures, because then the whole system's temperature increases. That means the particles were now moving faster. Number one, the faster they're moving, the more likely they are to collide. So that's the first thing. Number two, when they do collide, they're more likely to collide with sufficient energy. So what have we done? We've increased the chance of an effective collision. Okay? Now you're going to need to get the notes because I'm not going to write all of that down. We'll be here till Christmas. And I have put it in there. But if we increase the temperature, we are increasing the kinetic energy of the molecules. That means they collide more often, they collide with more energy, so the collisions are more likely to be effective. And an effective collision is a collision that results in products being made. And in the demonstration, that was us getting the orange stuff, okay, and the gas and everything else that came out. So that's important. By increasing temperature, increasing the number of collisions. Okay? Concentration. Now, with concentration, there was a question about what's the difference between mass and volume and concentration. Guys, concentration is defined as the number of particles per unit volume. Okay? Solids cannot have a concentration. So when I looked at the solid tablets, that's it. There's no concentration. Gases have a concentration, and liquids have a concentration, okay, except for water. Water is a pure liquid. But my sulfuric acid has a concentration, which means in any volume of sulfuric acid, if the concentration, say, is 0.5 mole per decimeter cubed, that means in every liter of solution, I have 0.5 mole of sulfuric acid molecules, H2SO4 molecules, okay? In the reaction, it's the sulfuric acid molecules that are actually reacting with my fizzy tablet, okay? So now we're going to say, okay, if we have an acid or a substance that's more concentrated, that means I have more particles. The more particles I have, the more collisions can take place. The more collisions that are taking place, the more likely they are that they are effective, okay, and that they have sufficient energy and that they collide with the correct orientation. So what we're doing with each of these factors is we're pretty much going, how can I make it more likely? How can I increase the chances of a good reaction happening? All right? Remember, I can't physically take, even though it would be nice, a set of tweezers and manipulate the molecules and change them around so we can change them so the orientation looks right. It's just not possible. We can't do that because they're too tiny. But if we make them collide more often, okay, they're more likely to get together. It's the same as you wanting to set up a friend with someone you know, and the first time you set them up, or the first time you get them in a room together, things don't quite work out, so you do it again, and then you do it again, and then you do it again, because in your head you're going, well, the more they get to know each other, the more they interact with each other, the more likely they are to like each other. It's the same concept, okay? The more particles we have, the more likely they are to collide. The more they collide, the more likely that is that the collision is effective. Please remember, grade 12, that obviously the opposite is true. If I decrease the concentration, I decrease the number of particles, which means there's less likelihood of a collision. Less effective collisions, it goes slower. Surface area. Now, surface area is the one that always gets us. So what I have here is a little bit of a diagram. This first diagram over here is the pink part is like my fizzy tablet. I know it's not round, but just bear with me, okay? And the like bluey, greeny color, whatever color that is, the little single dots, is like the water. When we have the whole tablet, the big tablet together, the only molecules that can take part in this chemical reaction are these ones on the outside. So these ones have to take part, they have to react, they first have to react, come off the tablet, and then the ones in the middle can start reacting. Okay? So it takes longer. There's less particles available for the reaction to take place, less collisions. However, when I break it up into smaller pieces, which is what I was doing when I made it into chunks, okay, look what's happening here. All of these particles are available. All of those are available. All of those. All of those. Can you see that if I had to now add up the surface area of all these little pieces, I would actually get a bigger surface area than my first time? So even though the particle, should I speak English for you guys? It's just a thought. Even though the pieces are smaller, and I know in our heads we go, that means it's a smaller surface area. Each individual piece is a smaller surface area, but when I add all the surface areas together, it's a bigger surface area. And that's the important part. And what is often said in the textbooks now is it's called state of division. Okay? That's like the new term that we need to use it for. I'm a little old school here, I'm afraid. Is we increase the state of division, break it up more, or we increase the surface area. Just like with all the others, if I increase the surface area, I increase the chance of an effective collision. Okay? Well, there's actually 3 more, but I put 2 more on here. Number 4. Now, these I didn't do with you because they're a little more difficult. The first one is pressure. Pressure only affects reactions that involve at least one gas. Okay? Pressure would not affect the reaction that I've just done. Now, I know I produce a gas, but I'm not concerned about that because this isn't a reversible reaction. When we do chemical equilibrium, that becomes important. Okay? So pressure only affects a gas. And essentially, pressure is just another way of changing concentration. So if we change the pressure on a gas by making the volume smaller, Boyle's law from grade 11, we make the volume smaller. So Boyle's law is Charles' law. Volume smaller. We're now taking the same number of gas particles, putting them in a smaller space. We're increasing the concentration of the gas. If we increase the concentration, we're increasing the rate of the reaction. It's the same as going from being outside on your school field, on the soccer field or the rugby field, and then being put into a classroom. Okay? Outside on the soccer field, you're less likely to find your friend wherever they might be, but coming to a classroom, smaller environment, you're absolutely going to be able to find your friend. Okay? It's the same concept. Smaller volume increases the concentration, greater rate of reaction, but there must be a gas. Pressure does not affect solids, does not affect liquids. Okay? So concentration only affects liquids, solutions, and gases, essentially. Okay? Doesn't affect solid. Surface area affects only solids. Has no influence on gases, has no influence on liquid, because we actually can't change their surface area. Pressure only affects gases, okay? Not solids, not liquids. Temperature affects all of them equally, so we're not too stressed about that. The next one is a catalyst, and we only use what we call positive catalysts at school. You get negative catalysts, they actually slow down reactions. But we use positive catalysts. You would have dealt with catalysts last year when you did energy of reactions, okay? And remember, with the catalyst now this is a slightly different explanation because now we're not talking about increasing the number of collisions because we make more particles available. A catalyst lowers the activation energy, okay? By lowering the activation energy, that sufficient energy that we need for the collision to take place becomes smaller. And if we have a lower expectation, so if we need less energy, they're more likely to take place, okay? So a catalyst always speeds up a reaction. A catalyst does not take part in a reaction. It remains whatever. If it's a platinum catalyst, it remains as platinum, okay? But it lowers the activation energy, which then speeds up the reaction because we're not changing the number of collisions. So if there were still, say, 100 collisions happening in 10 seconds, there's still 100 collisions happening in 10 seconds. But instead of that, before the catalyst, say out of those 100 collisions, only 20 had sufficient energy. Now I add the catalyst, and because it lowers the activation energy, now 40 have enough energy. Okay? So we still have the same number of collisions, they're just more effective. Because it lowers, they have more likely to have sufficient energy. Okay? Wow. Okay, we're not done. Hang in there.
Okay.
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 Okay, now we got the theory. Now we've got to do some questions.
Let's do that.
Let's do that. Okay. Now, guys, the nice thing about this section of work is when I was looking for questions, is if you look at where I've adapted them from, this is actually from 2001, and the other question's from 1999, and this section hasn't changed much. So if you have older siblings, or you can get hold of papers from the early 2000s or the 90s, really, this section's pretty much the same, which is quite nice. So here we have, and don't get like, oh, it's so much writing. I know it's a lot of writing. It's okay. We can do this. So it says to us, pieces of copper, which is there at the bottom of our test tube, are covered by an excess, too much, okay, so what that means is the copper determines how much product we get, of concentrated nitric acid in a test tube, okay? I'm hoping you've actually seen this reaction at some stage, though this gas is horrible, and if you get it on your hands, trust me, I know, it actually turns your hands brown. That's how I get it, and it's not a pretty brown,
Not a
like
pretty
a tan brown.
No,
It's not, and then it's not pretty. I've learned. Wear
nasty.
gloves. This is why people get worried when I touch chemicals. Anyway, so a reddish brown gas forms in the reaction, and it is noted that the contents of the test tube become hot. It's an exothermic reaction. The test tube is connected via a tube to a gas syringe, and the gas is collected in the syringe. So I can collect the gas in my syringe, which means I could also determine, look at volume collected per unit time. Anything to that effect depends on what the question would want. Now it says, how will each of the following changes in conditions, okay, so we're changing the conditions of the reaction, temperature, concentration, all of those sort of things, affect the rate at which the gas develops. So they're saying, will it make it go faster, slower, or make no difference whatsoever? And note, and guys, this is a little bit of an exam technique. It says write only increases, decreases, or stays the same. Please don't write an explanation. If you need to think it through, okay, and I know there's a lot of you out there, I have kids who are the same, who when they think it through, they actually need to write it down. That's fine. Do it on your question paper. Then on your answer sheet, only write increase, decrease, or stays the same. Because if I can't find your answer, I can't give you marks. And often, you go nowhere and you actually forget to answer the question. So you have this wonderful explanation, but you don't actually answer, and you don't actually ever say increases, decreases, or remains the same. So, first thing, more copper is used. Now we go, hang on, wait. Did we look at anything to do with the amounts in terms of reaction rate? No. What would change the reaction with the copper is if I changed the state of the copper. So if I went from, instead of using granulated copper, which just means it's bigger pieces, I used powder, or I made it into a solid chunk. But I didn't, I just used more. All that means is I'm going to make more product. But it does absolutely nothing for the rate. So that means this stays the same. So there's all this writing, and you write 3 words. Okay, 2 marks. Then they say to us, the temperature of the acid is increased. We've just spoken about it. If I increase the temperature, I will increase the rate. So that means this is increased. Okay, and then more concentrated HNO3 is used. Now we're going to go think this through, and we go, okay, they said to us that we had excess HNO3. This is actually really badly worded, because are they saying to us, and they would actually state this better nowadays, are they saying to us that we're just using more HNO3, so we're using a greater volume, or are they saying to you that the HNO3 is of a greater concentration? Makes it more difficult. With the context of the question, I think they're actually just saying they use more. And if they use more, it makes, sorry, my earpiece is just not happy with my glasses today. Just
Don't worry.
so you know. It's all right. Joe's are wearing glasses. I'm not fine. If we take it from the point of view of saying, well, I'm just adding more HNO3, then nothing, rate stays the same. Doesn't matter, because it was in excess. But if I take this to mean that the HNO3 is now more concentrated, so it's a higher concentration, then what happens to the rate? Remember, if we increase concentration, we will increase the rate. So it increased. Not so bad. And I think I have just enough time to do another question, which I deliberately put in because if you've seen the notes, you're going to go, hang on, wait, Tracy. You didn't do anything with graphs. It's what we call a little bit of extension. You guys can manage this. I know you can. Far too wordy. Doesn't matter. We have a beaker that contains a dilute solution of H2SO4, volume 140 centimeters cubed. The concentration of the acid 0.1 moles per decimeter cubed, temperature 25 degrees. Sodium carbonate powder is then added to the sulfuric acid solution to exactly neutralize the acid. Remember, you did acids and bases in grade 11. This is a type of question we could use there. The balanced equation is given. The reaction rate of the above reaction is investigated, and then we get the graph. So, this is a reaction rate graph. At the beginning, from 0 to 100 seconds, the rate right at the top, very fast at the beginning. Why? Lots of stuff in the reaction. As the reaction happens, we use up the reactants. The less reactants there are, the less particles there are, the less they collide. The less they collide, the slower the reaction. Okay? So it gets slower and slower and slower till it reaches this point, and now it stays the same. It's reached completion. It's finished. No more product being formed. And in fact, the volume here is the gas that's formed. Once that volume stays constant, no more gas is being formed. Now, the first question is, how long did the reaction between the two solutions take to reach completion? We've just done that. 100 seconds. Okay, over here. 100 seconds. Number 2. According to the graph, and I've also just explained this, the reaction rate is a maximum directly after the two reactants have been added together. Give an explanation for this. When they get added together, it's the time when we have the most number of particles available for bonding or available for the reaction to take place. The more particles we have, the greater the rate of reaction, because we can have more collisions. Okay? Now, last question. They say an identical sample of sodium carbonate powder is added to a solution again with a concentration of 0.1. Concentration didn't change. A catalyst is now added to the reaction mixture while the temperature is kept constant. All they're doing now is they're saying to you, I'm doing the same reaction, but now I'm adding a catalyst. I'm changing a condition. And then they give you this. And the question becomes, says to you, if graph 1, so the one I'm going to put in yellow, this one over here, represents the original conditions, the first graph, which one, 2, 3, or 4, represents what happens when I add a catalyst? A catalyst increases the rate of reaction. It has no effect on the final outcome. So it can't be 4, because 4 saying that I have a greater volume of gas. Never going to happen. So it's got to be 2 or 3. Now, rate of reaction, if we're going to add a catalyst, it's got to go faster, which means it's got to reach completion faster. It has to be graph number 2, this one. I'm not sure if you can see that. Let me do the green. This graph. Okay, and I'm about to run out of time. It's got to be that graph because it's steeper. The steeper it is, the faster it goes. Okay, gets to the same final concentration of gas because we used the same amounts of stuff. Okay, I think we've run out of time.
I think so. Have you finished your sentence?
I think so. I'm done. We're done.
Awesome.
Yes.
Awesome. So grade 12, thank you, Tracy, for such an awesome show. Grade 12, thank you for joining us today. I know that it really helped a lot. You guys were fully focused, so step back onto the page, read through all the awesome stuff that you've been saying, and I'm sure you'll be fine. I hope that all of you have downloaded all those notes that we gave you. Those notes are awesome, guys. I read through them myself, and I've sent them to each of you, some of you individually. So make sure that you download them, read them, print them, stick it up on your walls, and study hard, guys. Remember, learn more, learn extra. And, of course, thank you to Macmillan for sponsoring such a phantasmical show. Thank you, guys. Bye-bye.
we can say, well, the rate was 20 grams per second or 20 grams per minute or per hour. There's no set unit to rate, but it all depends on how we're measuring it. And how we measure it depends on the reaction itself, okay? So we can measure rate in 3 ways, essentially. 1, we can measure the rate at which a gas is produced, okay? And the way that we would do that, now, today I'm going to show you a reaction where we're going to produce a gas. We're going to produce carbon dioxide, I think. Yeah, we are. But I'm not going to collect it, all right? So we're not going to be able to measure the rate of the reaction based on the amount of gas produced because we're not going to collect the gas, okay? That would mean that we do it in a closed system. So say we're collecting hydrogen gas, we're reacting magnesium, say, one of your metals with an acid. The acid and the metal goes into a test tube, for example. The test tube has a stopper on the top with a delivery tube, which then goes either into an upside-down burette, okay, which allows water to go down because that would be a very small amount of gas, or into a gas syringe, which has the plunger, which is able to move, okay? And then we can see the volume change, and we can make a decision. Something like magnesium and hydrochloric acid, it's a fairly quick reaction, so we would take measurements every 10 seconds, every 15 seconds, etc. But if it's a reaction that's quite slow,
Hello guys, welcome to Learn Extra Live, grade 12s. It's finally your turn for some physical science, guys. I hope you guys are ready. Thank you to Macmillan for sponsoring such a phantasmical show. I know it's not a word, but it's my word for today, so I'm going to continue using it. I've missed you, grade 12, so much. I've been telling everyone else. I haven't told you. I've missed you guys. I hope you guys are already on the page. Most of you have been here since the grade 10 show and chatting to me. I really appreciate that, guys. Call your friends. Tell them to join us as well, because today we have Tracy in the house, and we are doing rate of reaction. Please tell us a bit of what we'll be doing today. Just a bit.
snippet. Well, besides the fact that I'm going to try not to blow up the studio
Okay.
a little bit later. Hopefully I won't.
Oh, you can.
Might get a little messy, but hey, my kids at least will go, no, that's the teacher we know. I'd say in love, but maybe not. But we're looking at rates, so we're going to look at why reactions happen in terms of their speed, and then we're going to look at the factors that affect that, which is what I'm actually going to demonstrate 3 of the factors.
Awesome. Thank you. So you guys heard it's going to be a jam-packed show with lots of, hopefully stuff will blow up and we'll see some cool things today, because I like seeing cool things and I know you guys like it too. So jump onto the page, facebook.com.
And it's the first link I put on there for the reaction of sodium thiosulfate. That's actually a really, really important reaction that you must be able to explain. Okay, sodium thiosulfate, when we react it with hydrochloric acid, turns milky because we create sulfur. And in fact, we measure, because there's no gas produced, so we can't measure mass loss. We can't measure gas produced. So we've got to find another way of measuring how fast or how slowly the reaction takes place. So what we actually do is we draw like a black cross on a piece of white paper, and we put a beaker on top of that, and either the sodium thiosulfate's already in the beaker, and then we add the hydrochloric acid, or we do it the other way around. It doesn't actually matter. And then we time until the cross disappears. This is a really nice one to actually do in a classroom, because when I do it with my kids, is we put the black cross onto the overhead. So I'll do it with an overhead marker, and then they watch until they can't see it. It goes a little bit yellow. We're creating sulfur, so you see the yellow for a while, and you know the reaction has finished or has gone to the same degree of completion. In other words, we've made the same amount of sulfur once we can't see the cross. It's a really nice way of measuring a chemical reaction. We're not going to do that one today, but it's also a nice one. You can see it with the links, and it makes it really easy. So there's lots of ways we can measure rate. The rate then gets described as mass per time unit, so
/Learn Extra, as well as our Twitter handle, guys. Make sure that you are here chatting to us, asking any questions that you need to ask. Guys, we're here for you. So basically, for the next hour, it's just you and us don't move off those seats because there's a lot for us to get through. Over to you, Tracy.
Oh, thank you. It's nice to be back with you.
I know.
I haven't seen the grade 12s for a while, actually, so it is very cool. Like I said, we're going to be doing rates of reaction. It's actually such a nice section. And what we're going to do is we're going to define and discuss what is the rate of reaction. We're going to look at collision theory, extremely important. We then are going to demonstrate some of the factors that influence the rate of reaction. And then we're going to discuss why. Now, unfortunately, I can only show you 3 factors. There's actually 5 that we need to look at, but we're going to explain exactly why they affect the rate the way they do. Okay? But now the first thing we need to do is define what we mean by rates of reaction. Now, the first thing we've got here is that the rate of a chemical reaction is a measure of how quickly or slowly a chemical reaction takes place. Now, that makes sense because we're talking about rates. Okay, and it's the same as when we say, well, power in physics is the rate at which work is done. So we're saying this is the rate at which the reaction happens. So we're looking at how quickly or how slowly. We know some reactions are really, really slow and some reactions are just really, really fast. We're looking at how that happens, okay? Now, there's a couple of ways rate can be measured. We can put it as a unit. So you know, taking every 10 or 15 seconds and you go, okay, 10 seconds gone by, oh wait, it hasn't moved. You then do it per minute or per hour, depending on the reaction, okay? And then we would write the rate in terms of volume, okay? Gas produced is very difficult to measure in grams, but there is a way. It's just a little bit more difficult, okay? But we can do that. The second way is to look at the rate at which mass is lost. But please note here, I've said in an open system. This would require a system where a gas is produced. So if we looked at the same reaction with the magnesium and the hydrochloric acid, and instead of just collecting the hydrogen gas, because that can be quite difficult, is we put it, say, in a conical flask on a scale. Okay? We put it on a scale, we zero the scale at the beginning of the reaction, or we don't have to, but we zero the scale, then it'll go backwards. But we can use it, put it on a scale, and we watch the mass change. Because as the mass changes, it means that the gas is escaping. And that is a measure of the reaction. So we're looking actually at how fast the gas is being produced. We're actually looking at the mass of the gas produced. But we would take it from the loss of mass, okay? The third way is the rate at which color change takes place. This one is actually quite important. And if you look at the notes we've put on the site and on Facebook and stuff, you can go to one of the links